Welcome to the short discussion on shear force and bending moment diagrams for the simple beams. This is part of the second unit, namely shear force and bending moment, right, in the course Strength of Materials 1. So I am hoping by the end of this particular discussion we are going to have, we will be at least able to draw the shear force and bending moment diagram for simple beams with point loads and couples, as well as with uniformly distributed load and uniformly varying load. So in this section I am going to focus on the approach of method of sections. Previously we had another discussion where we have used the simply the relationship between the load and shear force as well as shear force and bending moment. Okay, now we are not using the relationship, we are using the method of section approach, right? That means we are going to cut off the beam at section XX, either from left or right side, doesn't matter, at some distance, say X, and then based on that expression developed for shear force and bending moment, we are going to ascertain the values of shear force at every cross section. Okay, let's see how we can proceed that. So here is a simply supported beam. It is loaded with a point load at the center, exactly situated at the center, right? Now in this particular case, there are only two steps, I can say. With the help of these two steps, you can now find out the support reaction. The step one is the finding of the support reactions. So I am not dealing on this because previously I spent sufficient time for finding the support reactions, right? The essence of that is you can apply the equilibrium equations, right? Sigma mz equal to 0 at any one of the supports and apply sigma fy equal to 0. With the help of that you can find the support reactions. In this case, with simple understanding, you can easily mark the support reactions because the loading is symmetric. Therefore, the load will be shared equally to both the supports. So, in that perspective, we can simply mark the reactions without applying even equilibrium equations, right? So you can apply equilibrium equation when the loading is complex. It is having multiple loads acting, right? So we don't have to spend much time on this. Now the actual coming to the method of sections approach, basically the process of finding the shear force and bending moment in method of sections approach is we have to develop an equation at a section XX. So for that you have to cut a section beam somewhere at a distance X. You have to cut a section. So this cutting the section, right, you can take either from left end or right end in your convenience, according to your convenience, right? So that convenience in the sense your next calculations are going to be simple. In that fashion you cut off the section, right? So then again another point is, if you write an expression at the section XX, it is not that it is over, right? So in the sense the bending moment and shear force are varying from point to point, right? Not only that, there will be several loads encountering in between. Therefore, wherever there are new load coming, right, you are supposed to take another section there. So that means your number of sections is going to be depending upon the number of loads that are acting on the beam, right? So keeping these points in mind, let us proceed with this for this simple loading. So you cut a section at a distance x. So I have taken a section from left side at a distance x. I have taken a section, say x6, right? So now after taking that particular section, what I am supposed to do is I am going to write an expression for shear force at this section and bending moment at this section, right? For that you should have a basic definition, understanding of the basic definition about Vx and Mx, right? Shear force at a section X is nothing but the algebraic sum of the vertical component. That means at a particular section you are desiring shear force, you simply add the vertical components either to the left of that particular section or right of that particular section. Okay, that's the simple understanding. Similarly, mx, if you want algebraic sum of the vertical sorry, moment of the vertical components either to the left of the section or to the right of the section. Right? Once you are taking a section from left end, you forget about the other part. That means your whole focus is on this particular section only. Do not look at the other part of the beam. Okay, unless you take the section from that side. So your focus is on this only. So in your free body diagram, right? So when once your Vx and Mx is ready, right, you can easily get the values at any desired location. So for that, what I am doing is I am making a tabulary form. So here you have to portions or segments you have to take. This portion or segment, how many portions or segments you are going to take depends upon the number of loadings available. For example, here one loading is there. For one loading, right, I am taking two segments or two portions, right, because up to this the bending variation is in one fashion, right. After this, when because the load enter in between, I am going to take another section. Okay. Similarly, when there is only single load available running from such as UDL, so at that time we will discuss. So as of now, you are supposed to consider two segments. So first segment is up to center AC, and the second one is the remaining part CB, right. So here another point is that you can take the sections, right. Two sections you are going to take this half part of the beam one. Why half part? Because the load came at the half region, center region. So at this up to this one part, up to this another part. So you have to consider each segment separately, AC and CB, right. Accordingly, the free body diagram should be taken, right. So for AC portion, the free body diagram look like this. You have a reaction here VA, which is equal to W by 2, right. That is the reaction you got. Then you have the section here. Okay, so this is x distance, right. So now origin, always remember origin is going to be either left end or right end, not in between. Origin should be always either the left end joint or right end joint. So A you are going to take, and limits of the AC portion is going to be 0 to L by 2, and the shear force at the location, say Vx, is going to be how much? There is only one vertical component, so W by 2. And why it is positive? Sign convention is also important here, right? Sign convention we must follow. The sign convention is that here it was shown. The sign convention is when there are left of the section, upward should be taken positive. So you are going to get this value as plus WL by 2. Okay. Now at the same location, what is Mx? Mx is nothing but load times distance, W by 2 times X. Okay. Now the remaining part CB. For the CB part also remember your origin must be either A or B. So I am taking A. So when I take A as the origin, from A point C is at a distance L by 2 and point B is a distance of L. So the limit is going to be L by 2 to L. Okay. So then what is the shear force? The section now the free body diagram is when you are taking section somewhere in this location, the free body, that means X is your X is going to be whole distance. This is going to be your X. So this is your X. Okay. Then what is the shear force here? W by 2 already there, right? Previously whatever is value is there, that one minus, why it is minus? W came here and this is what downwards we are, when we are moving from left to right, you should take upwards positive, downwards negative. Okay, so when you are left of the section, downwards is going to be negative. So this is negative, W is negative, whereas W by 2 is upwards, so it is positive, positive and negative. That's going to be minus W by 2. Okay, so you got minus W by 2 in this region. Okay, and Mx as equal to the whatever previous value you got, Va times X. Okay, so this is previous value W by 2 times X, and what was this one? Minus W times, what was the distance here? X minus L by 2. So this was missing here. X minus L by 2 times. Okay. So this is the expression. Alright. So now you got the expression. Now you put the simply the lower limits and upper limits. You get the values wherever you want to draw. Okay. Then simply substitute the upper and lower limit. For example, the shear force is a constant value from 0 to L by 2. So from 0 to L by 2, simply put an ordinate of, this is L by 2 and this is also L by 2. This from 0 to L by 2, the ordinate is simply W by 2 only. So you can simply draw that with positive sign, W by 2. From here to here it is a constant variation. Okay. Then in the next region, CB region, it's going to be negative. That means it has to come down, right, to the negative region. So minus W by T. And in this region, it is not varying with X. Whatever may be the upper limit or lower limit, the value remains same. That means constant variation is going to be there. So this is going to be our value. This is the shear force diagram. Okay. Now bending moment diagram, as we mentioned earlier, always simply supported beam, bending moment at the roller support and hinge support is going to be 0. This is the first understanding we should have. Unless there are any couples acting, they are going to be always 0, because if they doesn't carry any moment, either hinge support or roller support. So if you know one more ordinate, no, you can calculate. Even otherwise, without this understanding also, you can use simple the mathematical expression. Put X equal to 0, it's going to be 0, right? Put X equal to L here. Okay. If I put X equal to L here, then also it's going to be 0, right? So either way also you can check it, right? So if I am interested to find only X equal to L by 2, that means I can substitute here or I can substitute here. Because this is from 0 to L by 2, this is from L by 2 to L. Anywhere I can put it. So if I put in this simple equation, W by 2 times X equal to L by 2, so it's going to be W by 2 times L by 2, it's going to be L by 4. So this is my ordinate, WL by 4. Then how to join? Previously, because it's a constant value, so I maintained a constant way. Okay. Now this expression you look at, this is like a y equal to mx format. So I am going to join with a linear. So straight line, join it. That's it. So this is your bending moment diagram. Okay. Here one more point you have to notice is, you can draw your bending moment diagram, the rest of the part, right, from this end also. Okay. That from this end also you can draw. That means for the segment CB, you can even or BC, you can say you can take the origin B and draw it, because that's going to be simple now. This here two terms are there, but here only one term. Okay. Sometimes it happens that you instead of drawing from only one end, you can use the other end also, because shear force and bending moment by definition, they are supposed to be calculated either to the left of the section or to the right of the section. Section you can take anywhere in that segment. So that using that simplicity, now if you form the again expression for Vx and Mx, Vx is going to be in this region, right? So you are on the right of the section. On the right of the, your section is here and you are on the right of the section. Right of the section, what is that? Upwards force. Right of the section, upward forces are negative. So this is going to be negative. So you are put on a negative side, shear force value. So you can join that. And then bending moment, as far as bending moment is concerned, W by 2 times this distance only. So the distance, if you want L by 2, so it's going to W by 2 times L by 2. Right? This is L by 2, this is W by 2. And sign convention you see. So what is the sign convention you are going to get this kind of moment. Your section is here, this kind of moment is going to be positive. So we can use plus WL by 4. So from this end also WL by 4, this end also WL by 4. Join it with a linear curve because it is also in the form of y equal to mx equation. Okay, a linear equation. You can get that. So if you draw exactly onto the scale, this is how it look like. Alright, now let's look at the uniformly distributed load. When you are having a uniformly distributed load, only one section is sufficient. You can take either from the left end or you can take from the right end. Of course, here also the first step is support. Without support reactions, unlike in cantilever, you can draw from free end without finding reactions. But here, support reactions are must. Here also because it is a symmetric loading, right? WL by 2, WL by 2. Because total load is W times L. Intensity is W, acting over a distance L. Total load, when you convert into a point load, is going to be WL, and it is equally distributed among the both supports because the loading is symmetrical. So WL by 2, you got it. Okay. Now, even if if there are different kinds of loading, a combination of loads, then you can use simply equilibrium equation. Sigma F mz equals 0, and other equation is sigma Fy equal to 0. With the help of these two equations, you can find the support reactions. Okay. So after getting the support reactions, here in this case WL by 2, WL by 2, so you cut a section. This cutting section, one section is sufficient here because the loading, same load continues till the end. So one section you can take either from the left end or from the right end, right? So if I take from the left end at a distance x, I am cutting a section xx. Okay. So now whenever you are expressing the shear force and bending moment at a section, you always keep that in the form of a concentrated load, a total concentrated load, total UDL you can say. Okay, total convert into total UDL. That means a point, you convert into a point load and put in the free body diagram. So if you convert into a point load, this is going to be like this. This part of the beam free body diagram will be like this. W times x, because it is acting over a distance x. So W times x, where it acts exactly at the centroid. So x by 2 on this side, x by 2 on this side. Okay. Now your origin will be in this tabulary form. You can simply make the calculations. Portion is AC. This AC portion. Okay. AC, or you can say AX. Why write AC? Because you can section can be extended till the end. The same load coming, and this section can be say BC, BX. You need not write AC up to not only center. You can write up to center also you can write. But you can write for the same load continues till the end, you can write to the L. So AX you can say, and that limits are going to be 0 to not even L by 2, you can even extend till the end. Here also same thing, you can extend till the end. Right. So your shear force now you can calculate. Vx is going to be, right, this value shear, this reaction we know, right, WL by 2 is the reaction. So till that point of the section, at this point first of all, and then we will come to this point, right? So at this point, what is the at the end? At x equal to, limits are what? 0. At 0, what is the value? Put 0 in this expression. So 0, so it becomes WL by 2. So the ordinate here is going to be plus WL by 2. Alright. You substitute the lower limit and upper limit in the expression of the shear force. That's what we are supposed to do. Vx is, right, WL by 2 minus Wx. Because I am calculating here, that is here. So what are the vertical components till the point xx? WL by 2 is upwards, Wx is downwards. So plus WL by 2 minus Wx. And in this I will substitute the lower limit and upper limit. Lower limit I will substitute. Upper limit if I substitute, right, upper limit, let's say I want to take at the center. So put x equal to L by 2. So it becomes 0. Exactly at the center it is become 0. So if I now, as I told you, this expression can be used even till the end. Say x equal, put x equal to L. Then what happens? If you put x equal to L, this is going to be minus WL by 2. So let us mark that, minus WL by 2. Okay. So I got this value also. Join that. Okay. This is a linear equation like y equal to mx plus c. So join with a straight line. This is your SFD. Alright. Then bending moment diagram, you have the expression for bending moment also. How? At this distance you want, at this section. So force into perpendicular distance, W by L, WL by 2 times X. So whether positive or negative, then go to the sign convention again. The sign convention says you are on the left of the section, right? This kind of moments are to be positive. So you got a plus WL by 2 times X. This is a positive moment. Okay, so once you got that positive value, okay, then next you have to look at the what do you call moment at the so this expression you got, right? WL by 2 times X for the first load. The second load, WX times X by 2, right? And this is acting no, in this direction, right? So this is the direction of that particular moment, which is going to be negative. So put negative for that. So minus Wx square by 2. So you substitute here whatever the limits you want. This is the expression for bending moment. So this is valid from 0 to L. Put 0, you get 0. This put L, then also you get 0. You see WL by 2 times L by 2. So how much is that? Sorry, L. So WL by 2 into L, WL square by 2, and here also WL square by 2. So it is also 0, right? So you don't have to just look at with simple understanding that roller support and hinge support always carries 0 moment, right? So at the ends of a simple support always you know the ordinate. So middle ordinate, if you know minimum 3 points, as we mentioned earlier, 3 points are there, then we can easily draw the bending moment diagram shape. So this center point, let us select that. Central point, if you put X equal to L by 2, this becomes WL by 2 times L by 2, that becomes WL square by 4, and here it is WL square by 8. So 1 by 4 minus 1 by 8 becomes 1 by 8. So this ordinate is going to be WL by 8 and a positive value. So are drawing on the upper side of the bending moment diagram, center line. So WL square by 8, you got it. Now how to join? Look at the equation. The equation is going to be a second order equation, a parabolic. So join with a parabolic curve. That's all. That is your bending moment diagram. Okay. So now on this exact to the scale, this is how it look like. WL by 2 and WL by 2 on the plus side here and then the negative side here, and a parabolic curve with a maximum ordinate of WL square by 8. Now if you go to the couple, a simply supported beam with a couple acting on the beam at some location, say at a distance A from the left hand and B from the right hand side. Okay, if this is the case, how to draw the shear force and bending moment diagram? Right, the procedure remains same. First of all, you find the support reactions, okay, using equilibrium equations which we have discussed earlier, and that reactions are, so here is the couple is anti-clockwise couple, so the reactions will form a this is a clockwise reaction, clockwise couple it form, because you can see this is going to be clockwise. To balance this, we require a reactions of the clockwise nature, that means left side upwards, right side down. Okay, so these things if you do not understand now, you can simply use the equilibrium equation sigma mz and sigma fy, right? You will be getting these values. So after getting the reaction, you cut a section somewhere, you cut a section here also. How many segments you have to take? Right, the segments you have to take is because a load coming in between. Up to this one section you can take, or one portion you can take. After this you can take another portion. So two portions, say AC, C is the central point, let us say AC one portion and CB another portion. For CB you can take the origin from B or you can take origin from A. Okay, so whichever is convenient for you, that means the last step you can use either this expression or this expression. Alright, so first of all what you have to do is, after cutting the section, you draw the free body diagram of that. So this is the free body diagram. So in this free body diagram, you can straight away mark what is Vx, what is Mx. Vx is nothing but algebraic sum of the vertical components up to the left of the section, right? Forget about the right part, we don't want. So once cut the section, that means you are to focus on the left side only. You are taken the origin from the left side, right? So you have to focus up to here only. So no forces are there except Va. So that is going to be our shear force at this particular section X6. So Vx is going to be Va, which is nothing but M by L. And Mx, if you want, you multiply the force with the perpendicular distance, that M by L times X. So that is your Mx. Then go to the no, this will be valid from 0 to L by 2, which means A to C. Now go for other part, right? So other part is CB part. For CB, I think it is easy to take from the origin as B, because the number of terms that are involved up to C from this side is going to be only 1. So you can take B is the origin, right? The limits are from this side. What are the limits? Where is the point C? From here 0 to say L by 2, or you can say, instead of saying the limits are actually slightly will modify, because it was wrongly typed. It is 0 to A here, because M is coming at the location A. Of course, it can be L by 2 when A is A is L by 2 and B is L by 2. Okay, and the limits of this one is 0 to P. Whereas the limits when you take origin A, the limits are going to be A to L. Okay, this is how it will change. Now, then 0 to L, A to L, and 0 to B. Now, what is the, you have taken a section here, right? This is the simplest way. Either you can even take from A also, doesn't matter. That also we'll discuss, don't worry. So if we take origin as B and cut a section here and draw the free body diagram of that, it look like this. The reaction is acting downwards, so it is M by L. Vb is minus M by L. If in magnitude, if you, direction, if you speak, no, Vb is minus M by L. So that's what we will write. Vx is minus M by L. No other force is there up to Xx. So we have to simply add up to the section Xx. What are the forces are there? Vertical forces. Only one vertical force, that is minus M by L. Why minus? Following the sign convention. You are on the right of the section, right? Right of the section. This is not minus, going to be plus only. Downward, right? Your section is here. Force is on the right side. This is the type of reaction. So this must be plus. This is a plus M by L. All right. Then your moment is going to be, what is the moment here? Moment is going to be M by L times X. This is the distance, M by L times X. Up to this, at section only we have to focus, whether it is shear force or bending moment. At this point only we are measuring. So bring the force towards you. So M by L times X. What direction is this? This is a clockwise direction. Right of the section, clockwise moments are going to be negative. Right? So if it is negative, then minus M by L times X. Right? Your limits are going to be 0 to B. Okay? So with this understanding, we can now plot the shear force and bending moment diagram. So first one, if you want to get the ordinate here, put 0 in this expression. So there is a constant term. So you don't have to substitute anything for shear force. Simply M by L is from 0 to A, you can mark it as M by L. So up to A, you can mark it as M by L positive. So keep it like that. Now, if you want the other portion in this expression, put a lower limit 0, upper limit B. So it does not vary with X. So straight away here also value, same value, M by L. So you can extend that till the end. So this is your shear force diagram, SFD. Now if you want to beam bending moment diagram, take the first expression, put lower limit 0. Okay, of course we already said in the previous loading also, always roller and support will have a 0 moment. Okay, so at A if you found out, then over, right? So at X equal to upper limit is, put X equal to A in this, then what you will get? MA by L into X. That means the ordinate here is MA by L. positive, right? MA by L. Next, take this particular one. So this side we are coming now. Put a lower limit 0, upper limit minus MB by L. So at this location MB by downwards I am drawing because minus na. So MB by L. Okay. So how to join? Right? Look at the equation. This is a kind of linear equation. Y equal to mx type. This is also y equal to mx. So join by a straight line. From here to here straight line. Then here to here straight line. That's all. This is your bending moment diagram. Right? If we draw exactly onto the scale, this is how it look like. Plus MA by L into A plus MA by L minus MB by L and M by L throughout. Okay. Now if somebody is interested to take, no, I don't want to calculate from the end B, I will move only one direction from A only. So you can draw that. You can also calculate in that way fashion also, right? Although it includes more terms, but the solution doesn't change, right? So M by L here. So you are taken a section in this region, but origin is A. As I told you, origin should be either from the left hand or right hand, not in between, right? So you take a section from A only, but in the portion of BC. So this is your whole section. So if that is the section, this is the free body diagram. Now Vx and Mx you can write. Vx is nothing but no vertical forces are there. So simply M by L, only one force that you can write. Upwards, but then upwards, therefore it is plus M by L. And then this one mx is equal to force times distance. So this is M by L times x positive. Why positive? Because you can observe the sign convention. Left of the section clockwise is positive, whereas M, you are on the left of the section, this is going to be anti-clockwise, so negative, minus M, right? So in this you put the limits, lower and upper limit, right? So a lower limit if you put MA by L minus M, simplify that, you will be getting MB by L, and put L, you will be getting 0, right? So that's all, 0 here and MB by L here, right? A simplification of this leads to minus MB by L, and that's what you will be getting here. So it does not matter whether you take a section from the left hand or right hand, your solution doesn't going to be altering anymore. That's the beauty of shear force and bending moment diagram. You can draw from the left hand or right hand as per your convenience. Don't make the calculations complicated and unnecessary. Okay. Let's see. Suppose you have now let's say we are drawing the shear force and bending moment diagram of the simple beams for triangular loading. The triangular loading is having an intensity 0 at either ends, at left and right ends, and having maximum intensity W at the center. For this case, how to draw the shear force and bending moment diagram using method of sections. Okay. So for this also, the first requirement is finding the support reactions, right? Here also it is a symmetric load, right? So you can simply write it, total load is half times W times L. WL by 2 is the total reaction shared to equally to both supports. So this becomes WL by 4, and that the other support reaction also becomes WL by 4. So if one doesn't understand this simple point, what you are supposed to do, you apply the equilibrium equations for finding support reactions. Okay, that is sigma mz equal to 0 at any one of the support and sigma fy equal to 0. Easily you will be getting these support reactions, right? Once you got the support reactions, you take now cut a section either from the left end or right end. See here, half part of the diagram is sufficient. You can take just a mirror image on the other side, you will be getting it. So one particular section, either you don't have to take two sections. Okay, one section alone sufficient because it is a symmetric loading. You can replicate that the other side. Okay, so for drawing the shear force diagram, take a cutting or bending moment diagram, you cut a section here and draw the free body diagram. When you express the free body diagram, remember that always convert to a point load. Don't write in the given loading pattern. Given loading is a uniformly varying load. Convert into a point load. How to convert that point load? You just find out what is the intensity here. The intensity of the load will be here at a distance L by 2. The load is what is that similar triangle principle you can use. At a distance L by 2 loading is W at a distance of X. How much? Okay, so it becomes W X by L by 2. That means 2W by L. Your intensity becomes 2W by L. Okay, now area of this particular one is nothing but the concentrated load, equivalent concentrated load if you want for this particular loading. Okay, see, don't look at the other part. Once you cut a section means forget about the right side. This is not there as if. So I am talking about only this part. Okay, so area of this particular one you find out. What is that? Half times L by 2 times the 2WX by L. So if you simplify that, it will be WX square by L. You will be getting. And where it acts? Exactly at the centroid of that. For a triangular loading triangle, the centroid will be at a distance of 1/3 of this distance from right angle, or from apex it will be at 2/3 of this distance. So x by 3. From x by 3, and because this is x we have taken, right? So this is going to be x by 3 and the remaining part will be 2x by 3, right? Now you can write expression for the shear force. So origin is E, we are starting from left hand. Limits are, this is valid from 0 to L by 2 only, remember, because after L by 2 the load is coming in up to this point uniformly varying, thereafter also uniformly, but it's getting reducing. So you can write only up to L by 2 safely. So your shear force will be WL by 4 up to, no, in this section, right? WL by 4, here is one more term missing, minus WX square by 2L. This is the expression for shear force. This is the expression. How? Add the vertical components, that's all. Vertical components going upwards, WL by 4. Right, left of the section upwards is positive. So plus WL by 4, and this is acting downwards, magnitude of WX square by L. Add that WX square by L, not 2L, sorry. WX square by L, right? WX square by L, right? Take that. Now put this lower limit and upper limit, you can draw the shear force diagram. So what is the lower limit? 0 you substitute. What is the upper limit? L by 2. So put L by 2 in this. So if you put L by 2, what is going to be? This is WL by 4 already, and this becomes L square by 4. So WL square by 4, right? L. Previously WL square by WL by 4, and now this is plus WL by 4. Now it is minus WL by 4, so becomes 0. So here at x equal to 0, WL by 4 plus, sorry, plus WL by 4. This ordinate is WL by 4. And at center the ordinate is 0. How to join? Look at the equation. It is a second order quadratic equation. X square term is there, joined by a parabolic curve. Remaining part, right? You can take a section if you like, right? Similar way, the same expression will come. What is the expression? Minus WL by 4. Here it is written. Okay, anyway. Minus WL by 4 and the same term, but with positive sign, WX square by L. As I told you, it is like a mirror image. Okay, here also put the lower limit and upper limit. Even you don't have to write, because it is a symmetric loading, you can replicate it on the other side. So from 0 to this value, W minus, this side is plus, so it is minus. You can join that. that is your WL by 4. So if you don't follow that mirror image and all, you can simply use the equation otherwise. Put x equal to 0 here, you will be getting minus WL by 4. Put x equal to L by 2, then you will be getting again 0. Because you are starting from this end, your origin is B, remember. You are taking a free body diagram of this part, okay, like the earlier one, Wx square by L, okay. Same thing you are writing here. Is not 2, sorry, is L only, Wx square by L, right? So you got this expression. Now if you want bending moment, okay, this also you can write, one equation is sufficient, second one you don't have to go, just to use the mirror image, okay. If those who don't get the understanding of the mirror image, you can just put that, no, form another equation, that's it. So 0 at both ends we know, so one value if you know, you can complete the bending moment diagram. So what is that one value? At the center, if you know, because in general, wherever shear force is 0, bending moment is going to be maximum. So at this location, we can find out. So put that value of x equal to L by 2. So what will happen? W L by 4 times L by 2. WL square by 8 here, and here W L square by 4. Okay, this is, what is that equation? Wx square by L, not 2L, this one. Wx square by L time, oh, half times. Okay, just a second. This is, yeah, we are finding the area of the the point load moment, right? At the location x. What it is going to be? W L by 4 times, this is the section we are taking. W L by 4 times x, this is correct. Wx square by L times, what is the distance? X by 3. Okay, so let's substitute that. Wx square, WL by 4 times L by 2. Okay, that's going to be WL square by 8. Okay, WL square by 8 minus Wx square by W times x square, right? That is L square by 4. We are putting x equal to L by 2, right? WL square by 4 into L by 6. Okay, simplify that and you will be getting 1 by 8 minus, that's what you will be getting, right? W L square by 4 into L by 3, right? W L square by 4, L by 2 by 3, L by 6, correct. So 1 by, what you will be getting, you can take common W L square by 8. So inside you will be getting 1 minus 1 by 3, that is 2 by 3. So this is going to be 2 goes 4 times, that is WL square by 12. So the ordinate is WL square by 12. This ordinate is going to be WL square by 12. Plus only, so draw on the upper side. So this ordinate you mark it. Join by all the 3 points, right? But already it is a quadratic curve. This equation look like a, this is a cubic equation. So draw the cubic parabola. That's all. So one particular portion is alone sufficient to draw the shear force diagram of a triangular loading, right? So exactly on a scale, if you draw, this is how it look like. WL by 4, positive and negative on this side, and maximum value of bending moment as WL square by 12 with a cubic nature, and here is a quadratic or square parabola. And finally, in the similar lines, you can draw the shear force and bending moment diagram for a triangular load with 0 intensity at one end and W intensity on the other end. That this cannot be left and 0 and right end. The same procedure can be applied if the loading is reverse, like here W and here 0. Same procedure can be adopted. One section sufficient. Okay, and remember here the calculation simplicity how to see always. When you take a section from the right, as we have an option for taking the section from left or right hand, you should always prefer in a simple stick, calculations involve a simple manner. So if you take section from left hand here, it is going to be simple. If you take from right hand, what is you will get a solution. It is not that you don't get solution. You will get a solution, but the complication will be coming in our computations. Okay. So whenever triangular load is coming, you should always take a section from the zero intensity, because triangular load may be varying, like this also it come, right? This is also triangular load. So when the load comes this way, you take section from the zero intensity like this. Okay, then it is calculations becomes very simple. Okay, let's focus here now. So first step is finding the support reactions, right? So I am not willing on that here because support reaction is separately discussed. So use the simply equilibrium equation, sigma mz equal to 0 and sigma fy equal to 0. You will be getting this reaction as WL by 6 and this reaction as WL by 3. Once after the reactions are over, you cut a section. As mentioned, simplicity purpose you all take from the left side. Okay. So you take one section is sufficient because it is uniformly going on till the end. One section is sufficient because no other loads came in between. Single section AX valid from 0 to L. Okay. Origin can be A, that is the left end. Okay. Now you take the free body diagram of this. So as I told you earlier, free body diagram you should always express in a single point load of the, or you can say equivalent load of the given loading. If point load is given, fine, but if it is UDL or UVL, you should convert into a point load and put here. So I am converting this particular load, uniformly varying load, into a point load that look like this. Okay, the uniformly varying load is look like this. So you put that here, then what happens? Your shear force will be Vx equal to, right, up to, we are calculating shear here. So whatever the forces, vertical components are there till that point of x, you simply add. So WL by 6 here, and your conversion here to convert in this particular UDL, right, up to this section. This is our section, right? Of course here it is x, anyway any one you can take, either this one or this one, any section you take. Okay. So that section if you are taken, and the area of this diagram is nothing but your concentrated load. Okay. So to get that you should know the load here first of all at the section. This comes from the simple similar triangles principle. Okay, or simply from the proportionate concept you can get it. At a distance L, load is W, at a distance X becomes Wx by L. So load you know, now you get the area of this particular, forget about the right part, up to section only look at half times Wx by L times half base into height, x times Wx by L. Okay, that becomes Wx square by 2L. That's what written here. Okay, so now your equation is going to be WL by X, shear force equation because WL by plus going upwards minus this term Wx square by 2L. So if you want to draw the shear force diagram, put the upper and lower limits, that's all. Upper limit, so lower limit if you substitute, okay, you will be getting WL by 6. So put that here. So this ordinate is plus WL by 6. Okay. On this side the ordinate is WL by 6. WL by 6. Of course you will not be able to see, sorry. I will write inside WL by 6, and this is positive. Okay. Next, if you want at some other point, okay, say L, minimum 3 points we are taking. So wherever you have equation with you, wherever you want to substitute it. So let's say at L if you substitute, what will be happen? L square by 2. So WL by 6 minus WL by 2 is going to be WL by 3, that is minus. So you will be getting this ordinate as minus WL L by 3. Join it, right? So join this. It is varying, from positive sides to negative side. Somewhere it is going to be 0. So if you want to find where it is 0, you put this equation to 0. That is WL by 6 minus WX square by 2L. So you will be getting, if you solve for x, L by root 3 you will be getting. So L by root 3 distance you are getting. So L by root 3 somewhere you will be getting 0.577. That means right after midpoint somewhere you will be getting. So this is the point where you will be getting 0 shear. Join these 3 points, your shear force diagram is over. How to join? Look at the equation. It is a second order equation. Join by a parabolic curve. Bus. That's all. This is the SFD diagram. Now bending moment, right? To find the bending moment at this section, force times the perpendicular distance, WL by 6 times x minus WX square by 2L, right? This force times its perpendicular distance, x by 3. So if we put x equal to which point we are interested, because anyway we know the shear force, bending moment at both ends. At simple support always bending moment is 0, as we are discussing all along. So 0 0, only one point if you know you can draw it. So that point can be preferably where the shear force is 0. That L by root 3 you can find out the distance is. So we found this shear force is 0 at this point, L by root 3, this distance. Okay, this is the distance. So put x equal to L by root 3 in this expression. Okay, you will be getting that ordinate, right? Possibly that ordinate is around WL square by 9 root 3. So this ordinate is WL square by 9 root 3. You can work out that and substitute here. Okay, WL square by 3. This curve is a cubic curve, x square into x. So this is going to be cubic variation. So I joined, that's why I joined with the cubic parabola. Look at the equation. Whenever you are having a doubt that which curve, whether I have to join linearly or I have to join quadratically, look at the equation. The equation same. This equation is a parabolic second order equation, so join by a parabolic curve. It is a cubic parabola equation, x cube terms joined by a cubic parabola. Okay, so exactly to the scale if you draw it, look how it look like, right? That L by root 3, what I am doing is this value, L by root 3 comes around 0.577 times, yeah. Okay, and this is the cubic parabola you will be getting. At this point you will be having a maximum ordinate. So that's all about the construction of the shear force and bending moment diagrams using the concept of method of sections. Thank you.